Welcome to another coding session where I create a new programming language from scratch. This is how the language currently looks like. And last week we added support for recursive types. So you can specify types like these. For example, this is either true or false. Types can have parameters or variables which are lowercase, and types can also be recursive. So this, for example, is a linked list. So it's either empty or it's more with a payload and then the rest of the list. And actually when you compile this, we compile that to C code, and it actually creates a linked list in C. Yeah, here's an example. We create a list containing some numbers, and then we get the center number out of that. So let's maybe run this. Yes. Okay. Yeah, so here we have a function for creating a list. There should be some other functions just like that. Yeah, here's another function, and up here is another function. And then the main function, which is here, creates a list using this list function, passing 3 numbers, and you can see that it returns a list of int. So here, because types are structural, they don't have an identity or something, they are just a name of some set of values. Here you can see that this returns either empty or more, containing an int, and this means this is a recursive type. So like start one type on the outside of this type, which is again this enum type. Yeah, and then we call this get function with the list and the index that we want to get. Fine. So yeah, we can see that this got compiled to C code, and we can actually compile that. We get some warnings, which is exactly what this session will be about, and we can execute that code. So why do we get warnings? The thing is, there are these cast expressions, and they don't handle recursive types well right now. For example, let's say that instead of this, we take some bool. It doesn't matter what bool it is, but yeah. The reason I'm not just writing true in here and then switching on true and false is that the compiler will actually complain that the false variant is unnecessary. But if we call a function that returns a bool, the compiler will see, okay, this, even though it is a comp time known value, the type of that is still an enum that contains both of these branches. Right, so let's assume our function returns, what am I doing? Yeah, kind of like this. Yes. It either returns a list of true and true and true, or a list of false and false. And then we get the length of that. So now, because types are like always the most precise type possible, the first case will actually evaluate to a list of true, and the second case to a list of false. And then only this, those get joined to a list of bools, essentially. And the way that's done is by upcasting these types. So we know we have an instance of this type, value kind of that matches this type. And we cast that to this type. This seems fine, but then the lowering from casts, like compiling casts, doesn't work yet. We compile tilecasts to see in a very straightforward way, but it's not correct. Yeah, here's our main function, and we can see that indeed there's a switch with two cases. And yeah, I know the function names are horrible and the type names as well, but it works. So yeah, here we create this, basically a list of true, and here we create a list of false. And then we want to cast those lists. And for the list of true, casting that list of true to a list of true or false means that we allocate memory for a list of true or false. Yeah, for this. And then we somehow need to convert that into this. And the way we do that is we switch on that. We see, okay, if this is an empty list, then we also want this list to be the empty variant. If it is the more variant, if there's more stuff in the list, then we set the tag accordingly and we copy the payloads. And you may wonder what's up with these tags. Basically, the way enums are represented in the C part is that they are struct with a tag and a union. And the tag just says which variant of the enum is that. Is that empty or is that more? So 0 means empty, 1 means more. And then each of these can have payloads. So in this case, the empty variant has no payloads, but the more variant, it has two payloads. It has a bool and a recursive type. And you can see that here. So empty has none, and more has some other payloads. So then you can see that you can, if you have an instance of this type, you can set the tag, and then you can say, instance.as, because that's the name of this union, .as.more, ._0, for example. You can use that to access the first payload. And that's exactly what we do down here in the main function. And here. Yeah. We say this is more, and then we set the payloads. So this right here. But here we do something weird. So this right here is an enum of, just true. So this has actually the type true. Whereas this has the type true false. And that's not correct, because these types don't match. And that's even worse in the false variant, I think. Because let's maybe look at this type true. Where navigating C with like type defs and stuff is kind of pain, but yeah, here maybe. So we have false and true, and these are both enums with only one variant. And in this case, 0 means false, and in this case, 0 means true. But then when we join them into a bool, we actually want those to have different tags. Yeah, right here. So here we need to distinguish between both variants, and that means 0 is true and 1 is false. So yeah, if we just copy the payload over, and before we had, a false thing, where the tag is actually 0, and we just assign that to something that's true or false, then this will be interpreted as a true instead of a false. That's bad. So basically what we need to do is, if we have a list of true and we want to convert that into a list of bool, we need to, traverse the list and convert all of the items individually. And this, yes, this is an expensive operation, at least sometimes. But I assume that in most real world code, you won't actually do this a lot. So I don't think it's very common to have a huge data structure of some type and then assign that to another type. Instead, what you usually have is that types are mainly like the most general type. Most of the variables often have the most general type, except when you just create a literal and assign to that. So, in this case, for example, we have our list of true and true and true and true, and sure, to convert that into a list of bool, we have to walk this list. But this is a small list literal, only 3 items. And I think in most other cases, it will be similar. You have either like small list literals like these, and then you immediately convert them into more general list type. Okay. Yeah. So let's look at how we deal with casts. And I think it's kind of, I think casts, they happen too late in the compiler pipeline. Yeah, let's maybe review the compiler pipeline. Yeah. All right. So here we have the compiler pipeline, and you can see that we start with source code. We then convert that source code into basically a representation of the indentation of the lines, because Martinaise, because breakfast is an indentation-based language. Then we pass that into some sort of abstract syntax tree, that's the toast. Then we flatten expressions into this expression guided graph, the egg. And finally we do type checking in the yogurt. Yeah, and the yogurt still contains these cast expressions. And that's actually, like, the yogurt is this right here. You can see that here are still cast expressions. So in the next step, when we want to convert that yogurt to C code, we kind of, this is kind of a weird place to do, to be doing stuff, because at this point we basically know all the types. We know that casts can be complicated, and they may have to be to do recursive calls and stuff like that. But still, converting that to C means we have to, on the fly, maybe create new functions and do stuff like that. I think the more elegant approach is if we remove cast expressions from the yogurt, and instead, while we are converting stuff and while we are type checking stuff, when we see, okay, we need to insert a cast here, we actually call some cast function that we then also generate. Yeah. So let's do that. Hello. Yeah. Let's do that. Let's do stuff in here. Yogurt. Okay, you know what? Let's actually just take out the cast operation and see where stuff fails. Yeah. Oh no. Line 380. Or something like that. Yeah. Here we push cast expression. Where is that? Okay. Right, when we encounter a switch, we make sure that all variants are handled. We compile all of the switch cases, then we find the common type of all of them. So for example, if one branch evaluates to true and the other to false, then the common type is the enum true or false. And then for each of the switch branches, we essentially add a cast. Okay. Cool. So I think what we need to do here instead is something similar to what we do when we call functions. If we encounter a call, so we compile all of the arguments, and then we look up a function, and then in here we say, hey function, we compile you to yogurt. We convert that function to yogurt, means we compile this function. And we somehow need to do something very similar. But with a cast. So we need to have some... No, it won't have this, or this, or this, or... yeah, it probably will have this. Maybe. Or we can say compiler with yogurt. Compile cast. Oh. Yeah, in the end, this will just be a call to, a cast function. The argument will be, this exactly. So what, basically here we map the branches. We have the old body with a very specific return type, and then we build a new body, which also contains the cast. And the result of the old body will be the argument to our call. Yeah. Cool. So call takes some other stuff, I think. It takes a yogurt call, of course, with this. A signature and arguments. That makes sense. So actually, let's insert that here. Let me remove these. Yeah, so I have a little bit more space. Okay, so here we insert a call, which will be the yogurt call. The receiver will be compile cast fun, maybe. Yeah, and we basically need two types, a from type and a to type. So it will compile to the common type. The type that is basically the old type, right? So what would that be? It would be old body case type. We already extracted that up here. Yeah, and this should return a cast function for this specific combination of types. So that we can then say, now I want to call this cast function where the argument is the old body. Okay, yeah. So now we only need to have this. And let's maybe create the signature of that down here. And alright, so we can compile built-ins, sure. Yeah, and here we have compile cast function. Takes a yogurt, which is a yogurt, I think, just a yogurt. And then it has a from, which is a type, breakfast type, and to, which is also a type. And it returns a yogurt signature. Yeah. Okay. Alright, this is called list. Sure. That's the first use case. And the other use cases will be pretty similar. So what's going on here? Here we have a function with some code. We compile the body of the function. Oh, I see. And then, if the function has the signature, it returns a bool. But then in the body, it just returns true all the time. At the end of the function, we need to cast that more precise type into the more general type that the function claims it returns. So let's do that here. Cast fun is compile cast fun from the, I don't yet know what, to the claimed return type. Okay. Okay, sure, this is the cast. It's just a call to this cast fun. Yeah. Argument is body.returns. Sure. So basically the body.returns, that's an ID, right? I think so. So then we need to get that thing. I think you can get the expression from the builder, I'm not entirely sure. Yeah, good expression. Yeah, this has a type, if I'm not mistaken. Okay, perfect. Yeah, and the type of this will be the claimed return type. Okay. Why doesn't this work? Push. You got fun. Hang on, how did that down here look? Builder .end.push. Because we need a mutable builder. Okay. Sure. Oh, look at this, we already have claimed return type and actual return type. So let's maybe not do this, but just say we need a cast function from the actual return type to the claimed return type. Okay, and then up here, oh yeah, this case doesn't exist. This works, nice. So then we need to create cast functions. And I think these will just be normal, like normal functions. Yeah. How does the function compilation work actually? So we create a signature. Oh yeah, this will be similar, I think. This is the yogurt signature. Okay, the name is maybe I don't know. Yeah, underscore cast from to something like this, perhaps. Why not? Yeah. Right. Params is supposed to be what exactly? Oh, yogurt param. Sure. And this is probably yogurt param. It's runtime known, and the expected an argument for the variant. Yeah, the runtime type of that is from. But yeah, actually, let's just say this. I think that's fine. Because those don't actually have to match the arguments. They are just there to disambiguate between different functions with the same name. But here, this should be unique already. Okay, so this returns a yogurt signature. Oh, yeah, that's actually enough. If we already have that function in the yogurt, you know, we just return the signature. Yeah. I think we can also do contains instead of checking is this some. Yeah. Okay, then we compiling cast from to much more descriptive. And now we want to do that. Okay, so I think, let's actually look at what the C part of the compiler pipeline does. I mean, it's not correct what it's doing, but at least it does something. Yeah, this right here. In case of a cast, we do this stuff. We have a source type and a target type, or from and to, and then we do some things. Okay, let's just paste that in here. I'm fine with that. And yeah, okay. So compiling this type to this other type. We have the types, that's no problem. If from is never, then okay, so this function should be able to call itself recursively. So I think we need to do something similar to what we do when we compile functions up here. Here we put in a placeholder into the yogurt. Yeah, I know this is some copy paste, but maybe we'll unify this, but probably not. Okay, yeah, we have a placeholder, sure. Nice. Nice, nice, nice. Cool. Cool. Okay, if from is never, then, well, this function will never be called, actually. I mean, yeah, in that case, we just want to return we want to essentially create an identity function. Or create a function with nothing inside. Like everything is fine in here. We can just return the signature and we're like, yeah. Oh yeah, but wait, this is weird. So let's maybe do this. If from is never or from equals to, yes. Then, and here we basically the conversion is the cast function is just the identity function. Okay. Yeah. And this, like, obviously to do. In here, we switch on the to. Yeah, MD2. Yeah, converting that. We'll do that later. First, let's look at how, like in the end, we need to put something in here. We'll probably have something similar to built-ins, right? Here we also build a signature, then we have, this function builder. That makes sense, I think. Yeah, this seems nice. Here good funds, put, yeah, let's do that. So here we have a fun builder. You got body builder, sure. The argument types, we only have one argument type. And that's the from type. To expression. Yeah, that's weird. It was a param before, right? So yeah, this is a yogurt param runtime. A runtime known thing is our parameter. We convert that. We say we return, you know, the actual body. So we'll create a new function, compile cast fun body, maybe. Yeah, let's maybe pass in the params as well and the body. Yeah, let's just do this. Okay, and in the end we just return the signature. Let's compile cast fun. the yogurt with the from, the to, the body, which is a body builder, and the params, which are IDs. That's a long argument list. Okay. This does not work. Why not? Oh, because we need the yogurt. Sure. Cool. Okay. So, compiling an identity function that will be, like, we'll take the first argument, I guess. Yeah. Okay. And we will we can just push stuff. Okay. I guess, yeah. Wait, does this return, like, oh yeah, a yogurt ID. I like that. The body, yeah, let's return a yogurt ID, the ID that should be returned. And if they are the same, by the way, param just needs to be a single yogurt ID here, because we know what kind of param it is. Oh, yeah, let's do this. Nice. Cool. So yeah, we have the param. Yeah, if the types are the same, we just immediately return the parameter and we're done. Otherwise, we need to switch on the type that we want to cast this to. If it's an enum, then we want to insert a switch. Indeed, we want to, I don't know, builder dot push yogurt up dot switch, something like this. Yeah, it needs a yogurt switch because of course it does. Yogurt switch with probably some stuff inside. Condition needs to be a yogurt ID, and that's the parameter. Yeah, we switch on the type, on the value that we gave in, and now we need to have the different cases. What are the cases? Well, let's see. We need to create a map from string to, what was it, yogurt ID, yogurt body? No, I'm not sure. Now let's maybe do that up here, so that we can then just do this. Cool. Cool. Try to assign, yeah, yogurt body. Okay. This call doesn't work because this is yogurt op, but it needs a yogurt expression because it also needs a type. The result will be the to type. So we basically do a switch. Fine. And now the question is, how do we, like, what do we do in the different variants, in the different cases? So basically, it will be pretty similar to this one. Oh, right. the target type may have more variants than the from type. So only for each variant in the from type, which needs to be an enum, which we unwrap because we know that to be the case, hopefully. Yeah. Oh, yeah. Hang on. Unwrap iter. I think let's just go with this for now. Yeah, for each variant, we don't need indices in here. Nope. Nobody nope. But this, yeah. Ah, look, there's a to-do in the C code. That explains why it's not working. Okay, so we have the variants. And we basically want to create the corresponding variant of the to type and also cast the payloads while we're doing that. So to is a breakfast type. Oh yeah, we already have the to variants, which is a map from string to type, I guess. Oh. Right, variant is probably, yeah, map entry. So the variant key that's the from variant. Oh, to let's call it just entry, but then immediately say we have the variant, which is the key, and we have the from payload, which is the value. And then we get the corresponding variant from the two variants, so we have both payloads. And now we want to cast those as well, and then create a new tag, basically. Okay, we can do that. We basically want to zip, right? From payload is a slice of something, of the different one variant kind of multiple argument payloads, basically, or multiple arguments. Yeah. So let's maybe take those. And here we have this. Oh, this doesn't work because it's a slice. What? Oh, without these, maybe. Yeah, okay. Okay, sure. We need to cast them. So let's maybe create, the cast payload. Maybe args. I think until now we always called them args, like arguments of a variant, which is maybe confusing. Maybe we'll change that at some point. But yeah. So what we do is we push a new thing in the builder, in particular a call. Yes, which will be a yogurt call with not a condition, but it's exactly a receiver, which needs to be a yogurt signature, if I'm not mistaken, which in our case will be, casting the from type to the to type. So yogurt.cast fun, compile cast fun. Yes. Up here with from and to. So this will be both.a and both.b. The argument, call it with something, is something. The payload, we need to get the payload somehow. Okay, we want to create a yogurt body. How does that even? Do we just create a new yogurt body builder stuff? Hang on. How does this work for the built-in things? Sure. For the switch. Here. Lower all cases. Yeah, we want to build yogurt bodies. Case is this. So we switch on the cases. Oh, this is a body, and then we could call to yogurt. I guess. Okay, but then converting, maybe let's put that somewhere. Cases means we do this. No, that happens for every case. Yeah, we have the parents, which is just that. Oh yeah, no, let's do this first. Okay. We have the variants, the from args and the to args. Sure. Then we build parameters for our body of our case. So for each argument in our from args, yes, this is a runtime known value of that type. Okay, then we convert the body somehow, which is exactly what we do here, inline, and then in the end we put that into this map. Okay, yeah. So the question is, how do we build that body? And that's what this case to yogurt did before. To yogurt of an egg body means, let's just do this. Okay, param IDs. So for all of the params, yeah, we don't have any mappings and stuff. So we say push, you know, this param. Okay, I get it. And then we have these param IDs. Do we need them? From, oh, I see. Yeah, so these are like the from args IDs. I don't know. Sure, let's leave that for now. Then we have the expressions, and in the end we create a body. Expressions is a list, and then instead of going over all of some existing expressions, we instead create a couple of calls. Okay, yeah, not this, but instead what we do is we do this. We don't have any mappings or stuff like that. We just do this. We want to map the payloads right now. Right, so for each, oh yeah, this is exactly what we do here. Beautiful. For both, we push some stuff into the expressions, I hope, and then do this. Nope, don't need to do this. Don't need to do this. Okay, hopefully this will work. And then the only remaining, like, I'm basically writing this code from like the outside in. If we have an enum, we want to create cases, and we need to iterate over the cases from the the from type and cast each of them into the to type. So we need to create a new body for the big giant switch that we're going to build down here. So the way we do that is by saving some parameters, sure, then saving the concrete IDs of the arguments, and then we want to convert those into, oh no, it has the same name, from arg IDs maybe. The from args. And now we want to do this, sure, but also have the to args IDs, which will be a list of qubit IDs as well. Then we now need to map those, and then we will add another expression. So here we'll put down the compiling, hang on. Ooh. Yeah, compiling a yogurt up dot. Is there something like tag or something like create an enum variant? Yeah, that exists. That's nice. Okay. So yeah, let's just comment this out for now. Yeah, because this needs a yogurt tag. And the yogurt tag needs a symbol. Nice. That's just the variant. And it probably also needs args. Oh yes. And these are the two arg IDs. Let us send this to blah 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 blah. Okay. Oh yeah, and this also needs a type. What was dollar? Where's my dollar? Here. And the type of that will be the to type. Yes. Okay. Yogurt expression. Oh. Okay, maybe we don't. Maybe we want to first do builder dot push. Okay. Okay. And it returns this. Cast. Oh. Params of the yogurt ID. Oh. Well, we do have these, right? I hope they are the correct ones. Yeah, I'm not entirely like sure about this code, but it's gonna have to do for now. Okay, so yeah, casting an individual enum payload is what we're doing right now in here. So in the end, yeah, this seems correct. We want to call something. In fact, we want to call the cast function. Correct. Yeah. From args. These are the types. Yeah, I guess. Two args. Yeah, let's maybe zip those again with the from args IDs. And let's maybe like extract some of these. So we have the from arg type. We have the to arg type. And we have the from arg, which is this. From arg ID. Okay. So here we just, it becomes more obvious. Here we just have the from arg ID. Okay. Okay, yeah. This doesn't work because the second thing is a list instead of an iter. Okay, yeah, this should work. Okay, then we have a giant switch. I mean, sure. Okay, and for the default thing, we panic. Ooh. Okay. Okay. Seems reasonable to me. Let's just try this out. Oh yeah, in the C compiler, we don't need to handle casts anymore because they don't exist. Look at how much simpler that gets. Whoa. Oh. Ooh. This is not pretty. So I guess we need to... Oh, right. When we traverse down into these types, like in here, for example, from equals from dot extend one level. Yeah, same with key. Maybe like this. Unreachable. To C. Well, that doesn't tell me anything. Oh, param. Of course it doesn't. Panic param should not exist. And body. Oh, but we should have yeah, we should have casts. Oh, look at this. Okay, yeah, casting an enum with only the true variant to an enum only containing the false variant. Yeah, it takes a value which is true, and it does this. Then it switches on that. If it's true, then we create that and return that. Yeah, okay. It does some other cast stuff. Oh, look at this. Casting a list of true to a list of bool. And this is, okay, this is super weird. Some params and stuff. And also these calls. I think all of this shouldn't exist. So we do something with these. Yeah, we have a builder, a yogurt body builder. Maybe for these, I think we should just create a new body builder in here. Yeah, probably. So this will be the case. Here. This will be the case body. This will be the builder.parent. Okay. So we have these. We have the params. We push those. Okay, I guess that's fine. Yeah. And here we should say case body or case builder maybe. so we don't need the expressions. Where are they? Here. Yogurt ID. Nope. Don't need them, don't want them. Yeah, and in here we just take the case builders body. Yeah. Okay. Cool. Cool. Let's see if this works. Okay, this actually looks pretty nice. Casting an enum with only the empty variant to an enum that has the empty variant and the more variant. And it just switches on the argument. If it's empty, then we create empty tag, but with this new type. Oh, this type got extended in a weird way. Do we only need to extend the from type? Nope. Well, okay. We have this. Sure. Oh yeah, casting true to true or false means we switch on that. Do stuff. Okay, so let's look at something, yeah, at this more complicated thing. A list of true to a list of bool. We switch on the thing, which is perfect. If it's empty, then we just create an empty tag of this crazy type. If it's more with these, oh, yeah, no, we don't need to add the parameters in here. They are implicitly there. Where does that happen? We have the from args IDs. Oh, here, we push these to the builder. No, we don't need that. We just do we? We don't. I think we don't. We do need to push into the fun builder. Oh, sorry, builder.count. Yeah. Perhaps this will work. Whoa. Seems like it does. Okay, but first let's marvel at this list conversion function. Where's that? Here. Okay, casting a list of true to a list of bool. We switch on that thing. Sure. If it's empty, we just create an empty tag. Ooh, if it's more with, you know, true and a recursive thingy. First, we call the conversion from true to bool. Perfect. Then we call the cast. Oh yeah, we call ourselves recursively. Makes total sense to me. And then we create a more tag which should have payloads. So let's add those. Tag. What do we here? Args is 2 args IDs. Oh yeah, we never add anything to that because the result of this call will be that. Okay, the case builder.push. Does that also return an ID? I don't think so. Okay, so we have the cast argument. Beautiful, maybe? Case builder.push. The fun builder returns the yogurt ID, sure. The body builder, oh, it also returns the yogurt ID. Okay, sure. Okay, yeah, so this was actually fine. And this also is also fine. Okay. Okay, so we make a call, and that is the cast argument. And to talk ID, we could do. I mean, sure. Why not? Nice. Where is that? Cast. Here, list of true to list of blip. More. Yeah. And here we create a more tag using not the true, but the bool that we converted. And also the recursive call to this other cast thing. Okay, let's see if the C code compiles. Whoa. Okay, that is some warnings. Pooh. I guess that's. Oh no. Okay, so functions kind of different levels of recursion in here. That seems well, kind of painful, but only kind of. Oh wait, no, this also doesn't make any sense. Converting this results in this, yeah, to archetype. Yeah, that, I don't know what it was. I'm probably copying stuff around. Well, okay, so we have an enum of empty and more of false. And an enum of empty and more of false. Okay. So while like this is horrible to read. So while casting this, let's maybe let's look at the C code. This, like, these are some types. They are okay. Ooh, like these are not minimal types or something. I don't like that. Okay. Crazy. Okay, does that work? It does. Okay. Okay. I mean the casts that we see in here. This should actually be fine because these are the same type. Like these types are exactly compatible based on how you use them. But still, adding more of enum, false, yeah. Was it like then? I want to see a simple thing. Yeah, this for example. Int function equals. Okay, let's do that. Int function equals. Yes, this function. Here. And there's also, yeah, 577 here. Okay, this does not work. Why doesn't it work? We have a type enum of less equal greater. And this built-in compare of 0 and 0 results in type equal. Hang on. Indeed it does. Do I want that? Do I want that? I don't think so. I mean, I like it should return converting built-in to yogurt. Like, yeah, it returns something. This, sure. But shouldn't it cast that to the more general type? I think so. Yeah. I think it should. What happens down here? We have the yogurt ID. We have this yogurt value int. I mean that's fine. Sub is fine. Compare is fine. But here we push the yogurt value symbol. Oh, convert it to an expression, and that ignores the type. True. Yogurt value to expression. No. This should be a yogurt up dot comp type value, but the type should be yogurt type, or like type ordering, like this. Yeah, it should not just be equal. This works. No, this should not be that. This should be a yogurt up comp time value, I mean sure, but of the type info. Is not as type info. I think so. I hope so. Yeah. Okay. Yeah. This is one piece of the puzzle to make this better. Okay. Well, there were still errors, but what's the shortest? The shortest error here. This is pretty short. Only 2 lines of error. So this seems horrible. Oh no, it's this. Oh, this is pretty small. Yeah, let's maybe do that. Okay, 508 in the generated C code. Okay, so we want to convert. Oh yeah, we have a list function that takes the value true of the type with true, and another true and another true. Sure. And it returns this right here. Enum of empty or more of true being recursive. Beautiful. So what's here? Cast. We want to cast this to that. Yeah, actually that makes sense. Yes. Okay, like the... Wait, but that's not the return type? Or what? Cast to empty or more of true. And the return type is enum of empty, more of true, and an enum of empty. Okay. So with cast functions, they should definitely return what they claim they return in the signature. That's one boundary. Like, if that doesn't work, then everything is broken. So we have the to type. Compile the body. We have these. Then yogurt funs put the fun, and this is a yogurt fun. Yeah. It doesn't contain a return value. Where does the C code get that value? Return type is, the returns expression. It has a type. This expression right here. So this returns something which is not this type. That's... I mean, okay, from never, we may need to create a cast for that, yes. Yeah, we should handle that separately. Otherwise, if from equals 2, then it's just the identity function. I get that. Oh, I see. Okay, sure. Oh. Yeah, we switch on the to thing. If it's this. Oh, okay. I think it makes sense to do that inline, because that's exactly where we are. Yeah. like at the last possible moment where we actually switch on a type, this is when we extend the type. Wait, it's a different result. Now the question is what result is correct. Hang on, what? It returned 2 before, right? Equals, oh, and this does return true, so it should return 3, yes. Wait, didn't it return 2 up here? Maybe. Maybe it did. Yeah, it returned 2. So it was actually incorrect. That's good to know. Okay, but now everything works, it seems. Even casting. What? Okay. Okay. I like that. Beautiful, kind of beautiful functions. Casting a list of false to a list of true or false. I mean, this is, I wouldn't say it's beautiful code, because obviously it's horrible, but it's nice that all of this casting stuff gets generated. Yeah. Okay, yeah, if it's empty, then this should also be empty. If it's more, then, well, first of all, we take this false thing. Nice. And we take the rest of the list, which is of the type empty or more or false. Then we create this bool thing, we allocate memory for that. We cast our false to bool. Beautiful. We cast, yeah, here we allocate memory for that other thing, and that we call ourselves recursively, hopefully. Yes, we do. Okay. Yeah. And then we create this other thing, yet again, of this type. I mean, that's pretty cool. Okay, casting values works. Yeah, that's like the main thing I wanted to do today. Because now all the type stuff works. Okay, let's actually like commit this and yeah, breakfast. Oh yeah, this works now. Yeah, but also I renamed the file extension from Camille to breakfast, and this. Yeah. Same here. Okay, so rename USBF file extension. And then here you can really see that the yogurt, it's so nice, just by looking at the code diff, you can see that the converting to C got a lot simpler, because we pushed complexity into the yogurt generation, not even into the yogurt. The yogurt also got simpler, but just compiling to the yogurt. We handle casts. Okay, handle like cast values correctly. Nice. I like that. Okay, yeah. I'm gonna take a break, and then we'll probably do some lightweight stuff, maybe some syntax stuff, like having comments, for example, or parentheses. Some of the things that were a bit annoying right now. We'll fix those. Okay. And I'm back. Yeah, next let's look at some syntax stuff. And maybe let's look at syntax highlighting first. So last week I tried to make that work by basically copying a VS Code extension from a previous project. Yeah, it doesn't really do anything, but there is this, what is the language configuration, where you can basically tell VS Code what is a comment, what kind of brackets do you have, so that if you type, for example, an opening parenthesis, that it automatically inserts a closing parenthesis, like this. Yeah, that's kind of what this does. And you can also see that, is there anything else? It has, yeah, it references this programming language grammar, which means that VS Code will actually parse this file, and then it will match these regex patterns. So, for example, if it sees an equal sign or a %, it knows, okay, this is an operator. At least I hope it does. And yeah, if there is something beginning with a quote, it will look for the ending quote, and everything inside of that will be a string. Except something with a backslash, and then one character after that. That will be an escape character. Yeah, there are numbers, there are uppercase names and lowercase names. That's what we have currently. Yeah, and this should cause VS Code to do syntax highlighting if it encounters a breakfast file. But let's just see if that works. Ooh. Okay, yeah, I think I'm going to have to open a new VS Code window, and then doesn't really do anything. Okay, you know what, let's maybe, strange. Let's create a new VS Code instance in here. Code. Oh wait, what? But code does definitely exist. Basically, because it didn't work last time, I reinstalled VS Code from Flat Hub, which worked, instead of the snap thing from Ubuntu. So this should do something. Okay, this runs VS Code. Anyways, yeah, I want to open the VS Code extension folder. So this is the same folder that we have here. But because we are in this folder, and there's a .vs code folder with a launch.json here, which says run breakfast extension. Now there should be, yeah, the option run breakfast extension. If we click on that, then we get yet another VS Code instance. Yeah, I guess that's fine. And here let's open the breakfast folder. Oh yeah, that's opened in another VS Code. Okay, so let's maybe just open the file. Hang on, open just like this. Breakfast test. Nope, not this test, but test.bf. Whoa. Okay, so we do have syntax highlighting. That's nice. Okay, so we have uppercase things, which are formatted differently from lowercase parts, and those numbers as well. Yeah, I'm using a Halloween themed color theme right now because it's almost Halloween, so we have these nice colors. Yeah, but in here the palette is kind of limited. So I think there's a inspect editor tokens and scopes. You can do that in VS Code. And then it tells you for each character what kind of character VS Code thinks this is. So this is a numeric constant, so it gets this foreground according to the color scheme. So yeah, as we move in here, you can see that this, for example, is a variable, correct? And this as well. And this is nothing, actually. Interesting. I would have thought that this was, I don't know, like a... I thought this would be an equal sign or percent or something. Oh wait, we have to like do this, right? To create a... I'm not a regex expert, but I think you need these parentheses. They kind of create a group. Oh. Yes. Ah, yeah. With or things in between. So like this. Probably. Not sure what the B is. I guess that's just... yeah, why not? Probably like a word boundary or something, so that if you have this in the code, then it won't get highlighted. I'm not sure. Yeah, let's just rerun this here. No variable. Then this is nothing. Well, that's weird. Maybe as hang on, I'm gonna check regexer, I think. Yeah. So let's just take this regex pattern, and I want to know what this means. Ah yeah, so that's what I thought. B is a word boundary, and then this is a group, and it's either an equal character or percent character. Okay, so hang on, if we see this, for example, I have no idea what this means. Global. Retain the index of the last match. Case insensitive, nope. Multiline, no, don't need that. Single line, no. Unicode. Sticky, what is... what if we remove these? Okay, now they match. Interesting. Yeah. Okay, yeah, maybe let's just do that. Oh, because word boundaries probably only work for words, I think. Yeah. What's the difference between this and this? Which is any character in the set. Yeah, that's more like what we want. Like this. Okay, let's reload this and actually go here. Hello. But nope. This is still, oh, it is. Hang on. Keyword operator. Oh, okay. So it does have some other syntax highlighting. I mean, it looks pretty similar to the rest, but sure. Actually, I think this acts more like a control keyword or something, you know. In here, when we have a var or a fun or something, or a switch, these affect the control flow, or they define stuff, and we want something very similar here. So I think we'll use that. Yeah, this is not an operator, but more like keyword. Oh, there's autocomplete. Nice. Yeah, keyword control, I guess. Or maybe split that up into keyword. Because equals is not really a control keyword, but just, you know, like a declarative thing. Whoa. Okay, yeah, this looks nice. Yeah. So these are really like, it makes sense that these are highlighted because they are kind of important, you know. The switch right here, that needs some attention in your code. Okay. Yeah, I think that's nice syntax highlighting for now. What else? I mean, in the long term, it probably makes sense to highlight functions differently from variables. Same if you call a function, for example. And maybe even highlight types differently. So t, for example, is also a type variable, so this should have the same color as maybe, I think. Yeah, so, but then again, here it looks fine. Well, yeah, we'll have to think about that. But I like this. These are not highlighted, but yeah, I guess that's fine. That is fine. And these, yeah. I mean, we can always adjust that later. So, okay. Nice. Now I want to do some syntax stuff. Oh, yeah. So I had an idea of how we could make things a little bit more a little cooler. Okay, so one obvious thing is allowing parentheses like these, so that you don't have to put things on multiple lines just to make a call. I mean, this looks ridiculous. Yeah, that's support parentheses. Yeah, this will not be here, but in the toast. When we pass type atom, for example, then we check, is there an opening parenthesis? If so, then we pass a new type expression which allows spaces inside, and then we consume a closing parenthesis, and we want something very similar for values. So I'm not sure, it's been a long time since I touched this code. When we parse a value, is that similar? Yeah, parse atom and expression. And here parse type atom and type type expression. Okay. Nice. Yeah, so here basically if we see an opening parenthesis, then we just want to pass an expression. Like this. Okay, so now this code should actually work. Let's see if it does. Okay, it passes at least, so that's nice. Okay, let's actually use that. And we're nesting. I think here we can just put that on the same line. Yeah, checking if the length equals 0 is this. But we can just put that on the same line. Okay. Same here. Yeah, so some of the code really gets more concise. That's cool. Okay. Yeah, let's run that. Perfect. Okay, so we support parentheses. Cool. Very, very cool. Next up. Yeah. So the pipe has meaning inside of types. And I think it would be nice to allow piping in values as well, but with a like completely different meaning. So for example, for me it's kind of weird that you have the outer thing first and then the inner things. In some contexts it makes sense, but in this, for example, I think it would be much more readable if the unwrap was at the end. So usually the way you would write this in something like Rust or Martinaise or something is like this. You know, you take a list, you get an item from an index and you unwrap that. And here we flip that around. We get something from a list, the index, at the index, and then we unwrap that. And this does make sense. And in Martinaise you can actually write this. You can write that, yeah. But having these, uniform calling syntax things with dot at the end is just a lot more intuitive. So can we do something like this here? We could do list dot get maybe with an index dot unwrap, but I don't like this. I don't. Do it like this? Maybe. I'm not sure. I think it does look kind of weird that this space seems more like separating than these dots. So it seems like this is called with this. Could just do this maybe. Yeah, that seems a lot more like we take the list, we get the index, we unwrap that. Or use pipes. Like in most functional languages, this is the thing, but I think that looks super bloated. This is a bit more minimalistic, but still retains that, that idea of we take this and we pipe this into some function. Because at some point I do want like struct fields, and something like foo.bar. Yeah. Yeah, I guess let's do it like this. And also, if these get long, you can even wrap them in multiple lines. Which does mean that we will need to unify the syntax a bit. Okay, I think it doesn't make sense. It also makes sense for the switch to be in postfix position. Yeah, because basically when you switch on something, that can be like an arbitrarily big expression, and what comes after is guaranteed to be this like multi-line thing. I think it would be really nice if you could, for example, I don't know, map this, like pipe this into something else that maybe returns an enum, so you can then just switch on this and be like, well, if this is some item, then I just want the item. If it's none, then I want 5 as the default. I mean, yeah, you would probably we would probably have a function for that, but still, I think it's nice to be able to like chain pipes and switches this way. You basically have your data and then make it flow through this pipeline thingy. Yeah. Okay, and for example, for this right here, it would then do, you could, for example, write rest. I want the length of that, and then I want to add 1, like this. That looks pretty clean, to be honest. That is pretty clean. Ooh, I like that. Okay, so let's do that. Let's support. Let's change the switch so that it's in postfix position, like this. Yeah. Similarly here, we check, does this index equal 0? Yeah, we need an operator for that, but well. We take the list, we switch on that. If it's empty, we do this. If it's more, then we do this. Beautiful. Ooh, that does mean that the syntax is no longer entirely tree-based, because now, in the tree of lines, yeah, and this right here, this and this, these are like completely separate expressions. They have nothing to do with each other because they have the same level of indentation. So we could, for example, say, let's indent this more. But then we have the same problem here. Percent kind of, sure, it can be empty, but it's more like we have this node, and then this is a child of that. And especially if this is like a multi-line thing like this, I guess. This is weird, that you have this. Yeah, I think, yeah, you could do this, for example, but that is like super verbose. Inside of these cases, you have like 3 levels of indentation just for a normal switch. Whereas in this, least there's only 2 levels. Yeah, I want this. This is more concise. It's nice. So I think what we really want is already in the bacon, like the compiler stage where we have separate, where we just have a tree of lines basically. I think there we already want to treat percent and this pipe and stuff like that differently. Yeah. This is really cool. Yeah, this doesn't work right now, I hope. Yeah. Yeah, this. No, wait. Okay, so yeah, before we do pipes, I'm just gonna adjust the way the switch works, because that should, like, that's like a smaller proof of concept to do this refactoring. So here we add the length of the list and 1. Okay, anywhere else? Yeah, here we have pipes, but really we want to unwrap the result of getting the index from the list, like this. We can even put that on the same line, because why not? Empty none. Oh yeah, this. Okay, but that's what we want to fix. Okay, so let me just adjust all switches to the new syntax. This is cool. Okay, so we have a bool. We switch on that. If it's true, we return false, and if it's false, we return true. Less indentation. Yeah. Like maybe the same level of indentation, but this was already refactored. Okay. This won't work exactly. Yeah. So we have the percent, and then we're like, oh, there's something coming after the percent. That's weird. Yeah. Oh, right. So, why can't I click here? This is like, I think my window management is kind of broken sometimes. All right, let's maybe first support parentheses. Well, I guess, yeah. So we have this. Yeah. Text-based diffing is kind of weird. Support parentheses. Not this, but this, yes. But also improve syntax highlighting. Cool. With that out of the way, let's look at switches. Oh no, we need to start even further here. Right, so right now the bacon is just all the lines of a file structured by indentation. Basically contains some syntax things. Leading pipe and flip are converted into kind of virtual lines. A tree that represents the file structure. File content is structured by indentation. Yeah. Each line maps to a node block in that tree. Some syntaxes leading some leading characters like simple flip are converted into also introduce new blocks that don't correspond to a line. Okay. Cool. Very, very cool. So we have a line and children. Let's actually like condense this code. Nice. Yeah, ongoing bacon, sure. We convert stuff to bacon. We look at the indentation. Yeah, we find ongoing bacon. Yeah, we find the node, which will be an ongoing bacon. And there we just append this line. And here we kind of need to handle these different yeah, we can do this. We can definitely do this. But then we should check is what's the first character, you know. Yeah. If line dot chars get 0, if that is a percent sign. Yeah. Create block, create extra block equals, oh yes, this, and later on we will also add more conditions here, like, or it's a pipe, you know. We can actually do that right here. line.chars.get 0 is pipe. Its first char is this percent, or no, first char equals percent, or first char equals this. Okay, and then if we need to create an extra block, then we do stuff, otherwise we'll just do this thing which we have done until now. So if we want to create an extra block, what we really want to do is we want to push an ongoing bacon, yeah, with the indentation of that line, true, where the line is only the first character. So basically, yeah, if we have, foo and this. Hang on. Ooh. Yeah, right now I'm just thinking about the part behind this, you know, like this. Foo. We want this to effectively become this. So we want to introduce an extra block for this and then treat the rest of the line as a child of that block and then append other children to that block as well. And I think the child should have an indentation of 2. So even in this case, for example, this would be passed as this. But if we had this, for example, then this would be passed as this. Okay, so if we want to create an extra block, then really we just want true. Yeah, okay. We want to create a line with only that character and with a single child. Yeah, which is an ongoing bacon, where the indentation is indentation plus 2. It just magically gets that. And the line is basically the line without the first character trimmed. Yeah. Cool. And yeah, the children, they are nothing. So an empty list. Okay. Cool. Very, very cool. Ooh. Yeah, I can even like factor this out into here. Because why not? Yeah, this looks horrible right now, but with a little bit of cleanup, look at this. Yeah, that's kind of nice. We don't even need this. Cool. Yeah, let's just try that. Ah, yeah. I mean, stuff won't work right now. Yeah, exactly. Oh, but we can see what the, oh yeah, this is cool. So really, although these are on the same line, like percent and the less part in here, they kind of introduce a virtual block that then has these children, which are all, you know, the same level basically of indentation. Oh, and here as well. Here we can just say, oh, I see. So here we have an empty child, and we don't want that either. So, oh, I hate that. Create extra block. Yeah. Okay, I guess. How do we do that? Yeah, basically if this is empty, then we don't want to add a child in here. Oh, okay. Not really clean, but is empty, then we just want an empty list as we want this. Yeah. Sure. Yeah. Better. Okay. That's pretty cool. Wait, but that means that we can, for example, also do this. Ooh. Clean. That is clean. Hang on, let me do that in here, where I have syntax highlighting. Nice. Very, very nice. Yeah, this is garbage. Okay. This is super cool. Yeah, so then in the toast, yeah, basically parsing, you know, kind of how, when we parse a call, for example, the way we do that is we just parse a single atom, and then we try to parse other things in a loop. And then if there are other things coming after, then we emit a call. Or here, we try to consume a special thing, like an equal sign. If that occurs, then we parse other stuff. And I think we need something similar on the block level. Like, where did we... Yeah, this basically. Instead of doing this up front, we would basically just parse, you know, an expression and the children and everything of that. And yeah, then do this. And then in here, before we return, we basically say, hey, is the next thing a percent? Then we want to parse, you know, basically continue parsing. And that's very similar to what we did up here with the parsing of well, anyways, of this right here. Yeah. So similar to how up here we have an atom, which is a self-contained type or a self-contained value without any spaces, except, you know, if they are in parentheses. We want something similar for these blocks. We want to be able to convert one bacon thing to this. Oh yeah, one bacon thing to that. Yeah, but when we pass, oh yes, this is correct. Then when we have multiple, ooh, yes, we do it like this. So here basically we iterate over the expressions and we pass an expression into, you know, this toast thing, and then we just check, is the next bacon in this line, is that just a percent thing? And then we wrap that expression in a switch before adding it to this list. So the expression that we get is, we have an initial expression right here. And then at the end, we just do this. But between those two, we loop. And the way we do that is by, I think this is not enough. No, we need to advance I. Oh, right. So bacons.get I or break if we're at the end, yeah. And then we have this. We try to pass, you know, a switch. And previous is a toast expression. And this could return a maybe. Toast expression. Pass toast switch. Yeah, something like this. And that just does this. Right in here. Oh yes. So that in here we can just say, well, first of all, I equals I plus 1 and expressions dot push the expression. And then here we say if the next thing is bacons dot get maybe I plus 1 or break. Yeah, and if next pass toast switch, where this is the current expression, if that is some wrapped expression, like this. And we will have something similar for pipes later on. You know, parse parse pipe or something. Let's maybe add that without actually implementing that, because I think that parse pipe, if some new, then we do this. Yeah. Oh wait, but I needs to be increased. Yeah. So here expression is new. Yeah, let's maybe do it like this. Well, kind of. The formatting is kind of weird, but I think it's fine. Yeah. Okay, so we look at the next expression. If there is none, we're done. And basically, if that is a valid switch, so it starts with a %sign and then it has some stuff, you know, we just assign, we use that as the new expression. And then we advance I and we try on those out of that to pass even more stuff. Yeah, otherwise if we pass a pipe, then we do that same thing, and if none of those passed, then we also break without increasing I. Yeah, that seems correct. Cool. Yeah, and then in the end we just pass we push the final expression to this list. Beautiful, beautiful. Okay, so then in here, we kind of, bacon line starts with this, or we return none. So if that doesn't contain that, and this would be the condition. This is not needed. That's cool. Making a line. Oh, and we know that these are actually just trimmed down. So this is only that because every leading percent is turned into a new block. Right, then we have the cases, and these are the children, and this is like exactly how we want that. Like this didn't change. Okay, and then in the end we return, yes, we could pass a switch. Perfect. Oh, true. Here we need a then keyword. This doesn't exist, true. So let's maybe add that fun parse pipe bacon, and let's call the left thing receiver, because that's usually how. Well, let's call it previous. Why not? I mean, receiver makes sense in languages where you send messages to one another, or like method calls and stuff like that. The true OOP languages, but in here it's kind of a misnomer. Yeah, and we need to implement that later on. Okay, yeah, I just wanted to have both of these so that down here we can have some code that generalizes. I don't want to, like, I know that I want to have pipes, so at some point. Okay, yeah, we have this. I think this should already work, to be honest. Let's just try that out. Okay, yeah, it seems like it does work. We have a new switch syntax. Okay, let me see one example of where we switch on stuff. Equals, yeah. We call built-in compare. Yeah, we switch on that. These are things. That's perfect. Okay. We have a new switch syntax, which is much cleaner, to be honest. Much cleaner. I love this. Okay, so yeah, let's commit that. A lot of stuff happened. New switch syntax, and also new enum syntax, because enums, no, but that's like a minor thing. New switch syntax. Okay, cool. Next, pipes. So I want pipes. First, let's try to implement types that go over multiple lines, because I think those are very similar to what we did right now. So instead of this, you should just be able to do list get maybe index unwrap. Well, I mean, this looks pretty sick. Okay, so parse pipe. Basically, we just want to do this. just want to see, hey, is this a pipe character? If not, then blah, we don't like that. Otherwise, we will... what will we do? I think we need to ensure that we only have one child. Yeah. Yeah. Because if you think about it, something like this is like this should not be valid. This needs to be an error. It should be indented like this in order for foo to be an argument to unwrap. Or, you know, it should be on the same line. That's also fine. So basically we just want to parse a normal expression, right? Parsed to toast expression. Yeah. Bacon.children.len equals 1. Pipe with multiple children. I know the error is horrible, but yeah. And then we just take the only child, convert that to a toast expression, which returns a toast expression, sure. And then it actually, what does it do? It should be either a call or a name or something. So either way we want to switch on this. Yeah. Oh yeah. If this is an int, pipe into int, that doesn't make any sense. If it's a, wait, what else is there? A string, yeah. Pipe into string, not valid. Symbol, oh yeah, this is actually valid. Ooh, it's kind of a weird way to create a tag, but I guess that's fine, yeah. How does that, do we have any like call? Where does this get created? Yeah, I'm writing this, I know. Toast call. Plus atom, okay, this is just any expression right now. Oh yeah, we can actually do that, I guess. Just have any expression there. Yeah, and just handle calls differently. Yeah. So if the expression is a call, we do some stuff. Otherwise, we just commit a call. Hang on. Like this. Receiver. Again, receiver is not a good name for that. Very OOP, very like object connotated, like well, okay, so if this is a call, then we basically want to return a call. Okay, yeah, we basically want to create a call which is a toast call of the call.receiver. Yeah. And the arguments, well, they are kind of weird. So we have a list of arguments, which for now is the previous expression. And then we say args dot Then we also add all of the arguments from this. So basically when you have a pipe in your code, the thing on the left, the previous thing, that becomes the first argument, and all of the other arguments, they come after that. Well, yeah, this is actually correct. Okay, and otherwise we just have the existing receiver, so call.receiver, and arguments is, call receiver, no, call is just previous, yeah, like this, and arguments is a list with a single argument, which is the thing on the left. Hey, hang on. No, this is the expression. Oops. Does that make sense? I think it does. Yeah, that needs to be put on the heap. Hang on. Yeah, that makes sense. Nice. We have pipes. Yeah. Simple as that. God. Okay, let's actually like organize this code a bit. Here we have int stuff. Built-in compare, I'm not sure. Built-in concat. We have bool, which is true or false, which is amazing. We have a not function. This looks amazing. We have unwrap. Oh hell yeah. You know what? Let's add an unwrap that takes a message as well. So an unwrap with a maybe and a message, which is a string, and it just does that. And unwrap without a message just does maybe, unwrap, where the message is that. We have lists, and we have, oh yeah, we can use concise. ABC, amazing. Yeah, len of a list. Oh yeah, so okay, here I want to use pipes, but I want to use them on the same line. I mean, for now I have to do this, len, and then we say +1. This should actually work. And it's already much more readable than the parenthesis thingy. We take the rest, get the length, add +1. Perfect. And similarly here. Take the list, check len, check does that equal 0. Yes. here, even here, you could just say, oh, yeah, let's like mix pipes and switches. We take the index, we check does it equal 0, and then we switch on the result. Nice. Very, very nice. Okay. Okay, this should compile, right? Cool. So what we did is we support pipes now, but only multi-line pipes. Next, single line pipes. So inside of a function, which is actually similar to how we do this, I think. Yeah. So if there's a trailing equal sign, then we create this thingy. Similarly, if the parser has a trailing pipe, then we want to parse an expression after that. Yeah. So parser.parse expression, or expected expression, there has to come something after that. Yeah. Sure. We need to loop that because you can have multiple pipes. And then in each of these expression will be wrapped into this. Yeah. Piped into this. And then, oh wait, we have some pretty similar logic to what we have down here, right? Down here. Where this is basically what we pipe this into. Let's factor that out. Piped call. Left is a toast expression, and piped into another toast expression, and this returns a toast expression, and it just does this. So if the piped into thing is a call, then we take the arguments is the left thing and all of the arguments of that, and then we create this toast call that way. Yeah. Otherwise, we just create that toast call into that one thing. Okay, so here we can just say piped call with the previous and the piped into thing. And up here, we can do something very similar. We create a piped call with the previous. Oh hell yeah. parses an expression without white space. Doesn't include white space, except in parentheses. Parses, yeah, we need to split that. Contain pipes. Again, except in parentheses. Parse, I don't know, unpiped expression. Something like this. Okay, so we have an expression. We parse stuff. We do this. The arguments. Yeah, and we don't have this. Yeah, but just, you know, basically this plus calls. Okay. Yeah, and then we have this, and this is just parse. Instead of parse atom, it does parse unpiped expression, so then it doesn't need this. Yeah, and when we have this, piped into is also parse unpiped expression. Yeah, because if we have one pipe symbol and some stuff, and then some other pipe symbol, we don't want, you know, those to be linked together. Like, assume foo, pipe, bar, pipe, bus. We don't want bar and bus to be piped together and then foo be piped into the result of that. But we want foo to be piped into bar as one unit, and then the result of that to be piped into bus. So when we reach this pipe, we don't just want to call parse expression, which would then also consume the other pipe, but we want to only parse unpiped expression, so that we only consume the bar, then we construct a new pipe, and then in the next loop iteration, we take care of that next pipe. Like this. Okay. Yeah. Parse.consume equals sign. I mean, sure, yeah. Let's try that. This, like, the code doesn't use that right now, but it should still work. Okay, cool. And now I should be able, and a nice syntax highlighted code, to use pipes like this. Boom. Let's see. Oh, nice. Very nice. Oh, yeah, so let's just use that consistently in our code base. Or like here, rest len plus 1. Nice. Nice. List len equals 0. That's the definition of it's empty. I mean, this is like actually a pretty readable code. We can also do this on the same line, index equals 0. I'm going to switch on that. Oh, what do we do here? No. We want, hang on, rest get maybe of index -1. Cool. And here we say list get maybe and unbreak. And yeah, you could put those on multiple lines, but I think in this case, this is fine. Unwrap out of bounds. Nice. that's amazing. We have pipes. Let's see if that actually works. Seems like it does. What? Yeah, just looking at the len function. Just double check that this indeed works. So we have a switch and then rest len plus 1 is what we want. So here we have a switch, and then rest len plus 1. Okay, so we first call len with the rest. Then we create a 1 and then we call add. Okay, that's perfect. Yeah. Cool. Yeah, let's commit this. Was it support multi-line pipes? Now support single line pipes. Okay. I think it's time to just look at, I don't know, the Martinaise standard lib maybe, and port some of those things. Yeah. Yeah, okay. Let me so yeah, this is another, never mind, okay. I think I can't open the standard library with it having syntax highlighting and having syntax highlighting here. Because, you know, for Martinaise it's very similar. The extension is not like packaged or anything, so it's still running an extension debug thing in another window, and we can only have one window open with Martinaise syntax highlighting, which is this window right here. Yeah, okay, you know, let's just open. Hang on, before we do that, comments. I want comments. Yeah. In the toast, when I convert, oh, I'm just realizing something. Comments can be super clean. Because this is indentation based, you can just say, this is a comment, you know, comment, and then in here, as long as it's indented, it still belongs to the comment. Like what? That is clean. Okay. To toast of bacon. Yeah, I think, do we want comments to be present in the toast? At some point, yes, because the toast will be used for, you know, for formatting. But I think for now, let's just omit them. Let's just say this returns maybe toast. Oh, sorry, not the entire bacon. Sure. But the, where's it? Yeah, to toast expression. Yeah. This should return a maybe toast expression. Yes. And here we have if parser.consume hashtag is some, sorry, just like this, then you say, well, no, this is just a comment. So comments will also be have the hashtag symbol. This call doesn't work. This is the signature. Oh, because this should be a mutable parser. Sure. And then in all cases where we call that parse switch, this call doesn't work because next. Oh yeah, because expression is we get the bacon to toast expression. Ah, yeah. Or if there is none, then we just, if this is just a comment, then we just continue to the next expression. That's fine. Similarly here, parsing a pipe. Basically we want a pipe with multiple children. Oh yeah. Yeah, this is actually, you can have multiple children if one of them is just a comment. That's totally fine. Yeah, so it should rather be yeah, let's just pipe, or like bacon dot children dot to, what is it, toast expression or something, expose, something like this. Yeah, and then just assert that there is only one, and then do this. Yeah, it's fine to have two children, a comment and a 3, for example, like a comment and I don't know what they call. That's fine, as long as the mapped children, there is only one of those. Yeah, okay, so let's do that maybe. Please still work. Yeah, okay. Cool. So now we can do this, for example, bools. Nope, couldn't pass the line. Bools. To toast of bacon. To toast of bacon. Here couldn't pass a line. To toast type def. Oh, I see. Or function definition. Oh, okay. I mean, sure. I'm fine with that. Couldn't pass the line. Okay. Yeah. Yeah, let's adjust the syntax highlighting as well. So we do have a comment pattern. I'm just gonna put that up here. So like a comment, yeah, a comment, a line, comment. Let's just say comment. Yeah. And actually, how does that look in Martinaise?
rows. There we have these comment lines. And sure, inside of the lines, to-dos are highlighted differently. Yeah, sure. Oh yeah, but there's also, ooh, I like that. You know, basically, if you have a comment line, but it ends with 2 spaces, then it is formatted differently. It's like a title comment, like what we have up here, or like for multiple. Hang on, type, yeah, here and here. So you can have these sections. I like that. So I'm gonna do that here as well. Yeah, hashtag and then some stuff, 2 spaces, and the end of the line is gonna be bold, but just a comment. And similarly for just a hashtag. Okay, yeah, is a hashtag a special character in regex? I don't think so. So I'm just gonna leave it like that. And yeah, this doesn't work with the indented comments and stuff like that, but meh. So what? The syntax hiding is not perfect, but at least this the simple case works for now. Okay, and with that out of the way, let's commit that. Support comments is what we did. Beautiful. Next up, yeah, actually porting the Martinaise standard lib. So Martinaise standard lib, I'm gonna open that folder. I don't really trust myself, but sure. Hang on, can I exit the Zen mode here somehow? Wait. Huh. Okay. So I'm gonna put that on the right. And yeah, our thing on the left. Ugh. Okay. Oh, no, we can't remove that. Kind of bloated UI. Yeah, sorry for the stream. I'm just gonna use less space. No, I'm gonna put this on the second screen and just copy stuff over. Yeah, that seems reasonable. So up here, first file in Martinaise is this. So in Martinaise, obviously, you can lower code, like you can write assembly directly and like rely on some aspects of the memory layout of types, and the calling convention is described here and stuff like that. And I don't think we need any of that. Nope. None of that is relevant in breakfast. Simple. Next up, bools. So we need to have bools, and we do. We have them down here. A type with 2 instances. Nope, don't have that. we don't have constants because you can just write uppercase true and false, and you immediately have a bool. Okay, so this is just a type with 2 instances, true or false. Cool. We have a not function. We do as well. Yeah, not takes a bool, returns a bool. True maps to false, false maps to true. Perfect. We have an equals function, which we're gonna name like this for now. Yeah, takes a bool and another bool and returns a bool. So it matches, it switches on the first bool. If that is true, then it returns B, else not B. You know, that's exactly what it says in here. Next, end. End of bools. What is that? We would just, you know, take our first bool, switch on that. If it's true, then it's B. Otherwise, it is just false. Nice. Next, or. And let's just copy this because, yeah. Or with 2 bools, if A, then true. If false, then B. Okay. XOR. So if A, then not B, else B. Beautiful. And finally, implies. Sure. Yeah. A bool, B bool. A true, B otherwise true. Okay, we have our Boolean operations. Then there is a hash thing, which, you know, for now I'm just gonna comment that out. Yeah, we don't need, we don't know how to write values yet and how to hash values. Oh, there was lazy and or. In a Martinaise that works by just implementing a function that takes just a single instance, the left side, and it returns a control flow, which then either says, okay, immediately evaluate to this value, or evaluate like the thing on the right side of the end. And yeah, we don't have that yet. I'm not sure if that's even, how would that even work? No, let's not do that. I think it's nice if like lazy computation is entirely visible in the program. Okay, that's it about bools. Next file from the Martinaise standard lib. Bytes. Ooh, and actually I think bytes are useful. They are, like, even in a higher level language, it's like, even if you don't control the memory layout and stuff like that, it's nice to be able to say I have a struct with this byte and this other byte, or I have, I don't know, a buffer of bytes, something like that. Yeah, so we will probably add bytes. Value from 0 to 255, yes, and all arithmetic operations wrap around. I'm not sure about that. To do. Yeah, bytes. I think bytes are just built in to the language, so they just randomly exist. so we have an add function. Let's call them a and b. A and b, and it just calls, well, that's the question. I think built-in add bytes, I think, of a and b. Yeah, no inline assembly. Very similar subtracting 2 bytes, multiplying 2 bytes, and dividing 2 bytes. Oh yeah, is this mod or remainder? I think this is actually mod. Yeah, so modulo and yeah, and with bytes. Sure. That seems useful. OR and XOR. Oh man. OR XOR. Compare. And finally to int. Yes, that makes sense. Takes a byte, returns int. Oh yeah, and all of these also need to return a byte, except compare, which returns an ordering, which we'll define later. And this is built-in byte, byte to int byte. Okay. Ooh, so incrementing and decrementing. I don't think we need that right now. Yeah. Bool has equals. Yeah. Let's add an equals function that takes a byte and b byte and returns bool, and it's just it calls compare a and b, and based on the result, if it's equal, it returns true, and the other cases like less results in false, equal and true, and greater and false. Hash, not sure. Copy, not sure. Writing a byte, ooh, with a radix. Ooh, char, now we know chars and stuff, and okay, fuzzing stuff, I'm just gonna remove that for now. Okay, yeah, so bytes are kind of a bit more complicated. But we have implemented bytes. That's cool. Then nothing, like the core thing. Ooh, so yeah. In Martinaise, there's the nothing type, which is just an empty struct. And I think having something like that makes sense. Yeah, no, this is not. No. Yeah, and this is just an enum with only one variant, nothing. I think that makes sense. Yeah. You can write a nothing, well, not really. You can compare a nothing. I guess. Why would you ever need that? I mean, I guess. Like this. Yeah. Okay. With this interesting function ignore that is generic over t returns nothing, like this. I like that. It's used to like explicitly say, I don't know, I have an if or something, or I have multiple branches, and in one I don't know, do nothing, in the other I pop something from list. Oh. Yeah, I don't know. I think it makes sense to have this. I'm not sure if I'll leave it in for now. Okay, so then there's never, and never is built into the language. Which means it doesn't really exist right here. Yeah, if you write a function that accepts an argument of never, it can never be called. Yes. Yes. Oh, well, no, those don't really exist. For example, crash. Oh no. Yeah, okay, but it doesn't actually exist. Also, we don't have and or keywords and no control flow thingy. So that is simpler. Floats, ooh. I'm gonna add maybe a to-do list up here. Oh, actually there is, hang on, there is a stdlib file. Just copy that over. Welcome to breakfast. Yeah, I don't know. And then just some to-dos. That's fine. Oh no. Like this. Yeah, I mean there are a lot of language features and so on, but I'm not gonna list all of them here. Because currently the language is in a state where it's totally fine to just work on something that's bothering me in the moment, and we will always have stuff to do. Okay, cool. So yeah, floats, not really. Okay, fuzzing, nope, hashing. To be honest, maybe we need hashing. But like hashing, how does that even look? You can say hash this. Like, for example, this doesn't make sense. I don't want a function to have, I don't want a mutable hasher, for example, because there is no mutability. This doesn't work. I think it makes sense to say that we can hash any value. Oh no, maybe now it doesn't make sense. We can't just hash any value. So we need a type. Hasher, maybe even a hash. You know, hash is init. Okay, that's fair enough. Yeah, I like that. And then here we have this I mean, what this really does is it has this hasher state and kind of combines that with other stuff. So basically I want to say combine this hash with this other value, or with this other hash, and it gives me a new hash, which will be something like this, you know, like a times 33 plus b. Does that make sense? Yeah. Yeah. Instead of a hasher, which is a mutable thing, we could say that this is actually like, you know, like a new wrapper around an int. It really, like, it's an enum that just has one variant, so it doesn't really make, it doesn't add any information. It's basically just an int, but it's marked as this is a hash. Yeah. And then you can explicitly convert a hash to an int. Which switches on the hash, it only has one variant, and then it returns that content. That seems weird. Okay. Does that make sense? Does that make sense? Because this things I don't want. No. Let's just say hash is an int. Yeah. Combine hashes. Yeah, that's fine. We have these. Yeah. Initial hash. That's. I mean, sure. Oh, I see. Add hash and int. Okay, yeah. Oh yeah. I have a type hasher. Which is just that. Yes. And we don't have global. Oh, okay. Yeah, I guess this is. No. This is fine. Okay, this is just a hasher. Sure. Oh, like this. I think this works. basically like a function that takes no arguments. And we can add an int to a hasher, returns a new hasher. It just takes that hasher and value, and it switches on that hasher. This is guaranteed to be a hasher with a state. And then it returns that state times 33 plus the value. And all of that in a hasher. Right. Oh yes. Times 33 plus value in a hasher. Yeah. That is basically this. Yeah, we don't have iterables. Maybe we'll have them at some point. Okay, but now you can basically say hasher is initial hasher, and then hasher equals hasher add 1, add 2, and you will probably create more add methods so that you can then at some point also say add hello or something. You can add all of those to the hasher. Then in the end, when you say hasher finish, you get a hash. Yeah, this. And that did what? It takes that times 33. So just this. Okay. Cool. Yeah. But yeah, hashing is kind of weird. Okay, next. Ints. Boom. We do have ints down here. Well, this part. Yeah. Okay, int is not defined because it's a built-in type. Oh yeah, min and max, and they probably makes sense to have something like this. But I'm not sure about how exactly ints are lowered and stuff like that, so I'm just gonna leave it like this for now. Yeah, exactly. You can add ints, you can subtract ints, you can multiply them, divide them, take the modulo stuff, which will be pretty similar to what we did up here. Except all of the Okay, so there are built-in functions for all of the common operations, including AND, OR, XOR, shift left. Wow. Oh, that's actually implemented in code. Sure. Shift left. A int and by int, which has a new int. What does it do? Basically, by times it multiplies that times 2. That makes sense. So I think it makes sense to compare by with 0. If by is 0, then we just return the end. If it's not 0, then we call shift left. Oh yeah, we multiply that with 2 and then call shift left with by -1. Yes. I mean, sure. Similar shift right does the div. This is the power. Let's see a base and with the exponent int returns an int. What it does is it oh yeah, there's a more efficient way to do exponentiation, but yeah, for now I'm just gonna have a power rec where we have a result, a base, and yeah, and basically it just starts with 1, so this just calls yeah, mapping these two recursive things is kind of difficult sometimes. Yeah, basically we check is the exponent 0. So exponent equals 0. If it is, then we just take the result. Otherwise, we call ourselves recursively with the result times, here it is, times the base. And the exponent -1. Yeah. Okay. Then an absolute function, abs of an int, returns an int. What does it do? It basically says, hey, I want to compare int. I want to compare int and 0. If the int is less than 0, I just want to return the int, so 0 minus the int. Yes. If it's equal to 0, I just return 0, and if it's greater, I want to return the int itself. We can probably simplify this as soon as we have a greater or equal than operator. Okay, round up to multiple of. Ooh, that is nice. Okay. Round up to multiple of number int. Factor is an int, returns an int. What does it do? Well, it just takes the number, adds the factor, subtracts 1, divides by the factor, and then multiplies by the factor. Obviously. Oh man. But no parentheses needed, because, you know. Okay. And then we round up to the power of something else. Okay, yeah. This will be similar to this, by the way. So, round up to power of, yes, we start with the power 1. We have the base and the factor. Yeah, okay. So the way this works is we basically compare. Oh, is big enough equals. We'll basically compare, comparing the power and the base. Number. Is this code correct down here? For example, if a number is, I don't know, 3 dot round up to power of, oh, I see. Yeah, it is correct. Yeah. Because this is not really a base, it's just a number. You compare the power, the current power to the number. Yeah. If it's less, then it's not big enough. If it's equal, yeah, then we are done. If it's greater, we are also done. And then we're basically, if this is big enough, then we just return the power. Otherwise, we call ourselves recursively, and power is power times factor. So yeah, basically result times the factor, correct. Yeah, then the base, or the number we want to reach, and the factor. Yeah. Oh shit. Okay, square root. Square root of a number is what? Basically we may want to do something like this in the future. Oh, this is potentially inefficient. But you know what, I'm fine with that. Yeah. This like really just calls square root rec, where the candidate is 0. Oh yes. Square root of 0 returns 0, okay. Yeah, okay, candidate is 0, and then we look. We have the target. Yeah. So we have this with the candidate and the target returns an int. So what it does is it basically checks if we were to increase the candidate by 1. Yeah. Next is candidate plus 1. Next, yeah, I don't know. Next times next gives us a number, and we compare that to the target. Oh yes. If it's less than the target, then we can safely say that we want to call ourselves recursively with the next candidate and the target. If it's exactly the target, then we can just evaluate to that candidate. And if it's greater, then we want to return our existing candidate. Yes. Okay. Oh yeah, there are a lot of functions in here. Like really. And then IO stuff and well, okay. Yeah, I'm gonna take a quick break and then continue. All right, square root, we've done that. Log2 is the next function. Do we need that? Perhaps. Yeah, I guess. So log2 of value returns an int, and basically we can just check the value, right? Does the value equal 0? If yes, then oh wait, no, 0 is invalid. If the value equals 1, then the result of that is also 1. Him a logarithm skills show. Oh no, the log of that. Log of 1 is 0. Yeah, and the log of e is 1. That's... yeah, okay. So this is 0. Then there is the case what if it's not 1. Okay, it's bigger than 1. In that case, we basically want to do log 2 of the value divided by 2. And then add 1 to that. Nice. So much shorter than this down here. I like that. Okay. Cool. We have comparison, which is implemented in the compiler. Yeah, compare ints. That's fine. Oh, it returns an ordering, right? Yeah. Cool. Copying a value doesn't even make sense because we are in a functional language, so the value can't change once created. Increment, decrement, no, don't need that. Equals, we have that right here. Oh yeah, lower byte. Ooh, that should probably be built in, I think. So we have an int, want to return the byte, and this could be in lower byte of int. Yeah, something like that. Then there is the equals function, yes, parse int. Ooh. Not the highest priority thing to do, I believe. Yeah, writing ints, okay, sure. Having a radix and writing an int with some radix, I mean, I guess that's very specific. We need to think about how to do writing and buffers and stuff like that. Okay, so let's see what else is there in Martinaise. There is like I/O stuff, you know, like files and printing things and standard error things. There is iterating, which I think requires, yeah, this definitely requires closures, which we don't have yet. There was JSON, which is quite advanced. We have simpler stuff to do, like lists and maps and so on. There was list, which is a growable array. Yeah, instead of our linked list. Generate, yeah. Okay, yeah, let's maybe have a rough idea. Okay, so the following plan. First, I'm going to look at ordering, you know, so even like before hashing, and the order of this is kind of weird. Well, okay, so let's do this. Let's create not really. Okay, so an ordering is just less or equal or greater. Okay, you can compare them, sure. You can hash them. I guess, yeah, but like I won't. You can write that, sure. You can flip an ordering. That's interesting. Let's do that. Oh, like this is, just compare this. This is super concise code. And just imagine how that would look in Rust. They would have like stuff like this. Well, no. So much bloat. Yeah, I don't know about how will I implement operators. Ooh. Not sure. Not sure how I'm gonna do that. Well, okay. Maybe let's trim things down a bit. We have bools. I'm happy with that. We have bytes, which are fine, but I'm gonna move them further down to here, maybe. Yes. And bools, I'm gonna move them here. Yeah, that seems cool. Okay, so we have the standard library. We have nothing, which is just an enum with only one variant. We have never, which is defined by the compiler. We have bool, which can be true or false, and we have several functions you can use. Then we have comparisons, like ordering and flipping and ordering. We have hashing, which is not really needed right now. I'm just gonna, remove all of that. Okay, but then we have bytes and we have ints. Bytes we don't really need yet, I think. Ints, okay, sure. Then we have several int functions. Okay, yeah, then we have strings. We have maybe. We have lists. But these are really like linked lists. And then in here, actual program. Okay, yeah, so above that is basically like the standard library. We don't have multiple files yet, so, you know. So let's just see if all of that parses. Probably not. Yeah. Okay. Well, this doesn't tell me anything. I'm just gonna comment out everything, like everything. Okay, yeah, there is no function in main. That is what I expected. So maybe let's just add the bool functions and those parse as well. There is no function in main. Oh yeah, I see what's going on. So here should be an equal sign, right? Oh, it does stuff. What is it doing? Shouldn't be like this. Yeah, it's kind of stuck. Probably an infinite loop, perhaps. Okay, hang on. We have the bacon. Boom. And then the parsing goes on forever. Okay, that is weird. Alright. Yeah, let me just open up breakfast again. And oh, different theme. Why does it have a different theme? Where's my Halloween theme? Ooh. I don't know which one it was. That's kind of a bummer. Oh, now it's changed everywhere. Well, I guess let's not. Why? VS Code is just weird sometimes. Just weird. This is kind of cozy. Sure. Okay. So we parse forever, which means in the toast there is some infinite loop here. And the question is where? And why? Like if I just where's the file? Here is the file. Yeah, like if I comment out most of this stuff, this will still work, right? Well, we need lists. But apart from that, and equals for ints, where are the ints, bytes, int. Equals. Yeah. Takes forever. Why? Okay, let's comment out all of the other int stuff. And just do this. Okay, bool doesn't exist. That is correct. Bool does not exist. So let's change that. Add back the bool. Okay, so now maybe doesn't exist, which is also correct. Let's add maybe. Okay, there is no function in plus, which may be true. Oh yeah, we have equals, but we don't have plus. Of course, we want a plus function, and there is no built-in function and built-in add ints. Okay, that is correct. That is correct. What about these functions? I just want to see which function causes an infinite loop during parsing, you know? Huh. Okay. Some of these. Interesting. Why? Oh, this should be right, I think. Shift left gets paused. Okay. Shift right gets paused. Okay. Just this power recursive function takes forever to parse. Okay. What? Why? Maybe if I don't do this. Still. What? There is nothing inside. What about then? What? This doesn't make any sense. Okay, let's look at this. Power rec result is an int. Base is an int. Exponent is an int. Returns int. What does it do? Well, let's say it just returns nothing. How? Why? Okay, I'm gonna add a log thing to parse expression. Parsing export rest is parser.rest. Does that exist? Nope. Nope. Okay, so parser.input. Nothing. But then there is nothing. Okay. toast express. Oh, is it this maybe? Yeah, if we have a comment in there, we also want to increase I, of course, like this. Yes, okay, cool. Oh man, yeah, comments inside of function bodies just didn't work at all. So this should work, right? Candidate. What does it say? Expected error. Somewhere in this area, but here's an error. Here as well. Not sure. I'm not sure. Yeah, we do need error reporting with the concrete line and stuff like that. We should add that. I'm not sure if now is the best time for that. I mean, I guess does this work if I don't have this? No, same thing. Okay, so here is something. Oh wait, probably can't have 2 in the function name. You know, sometimes. Okay. So we have these. These are commented out. Okay. This. Yeah, we want ordering. Let's see. Okay. Yeah. True. Byte doesn't exist. Okay. Yeah. Now the next question is, in which order do we add, you know, new types to this? And I think the main way would be to where's byte even? I think in int there is like a lower byte thing. Yeah, let's just comment out that. Okay, yeah, so there is no function named built-in add-ins. Yeah, so all of the built-in functions, we kind of need to add more built-in functions, add more built-ins, think about how those interact. Yeah, I'm gonna do that later this evening maybe. Yeah. Okay, but we've created a foundation for the standard library, and it's nice to have something that you can work and like iterate on, you know? And over time we will be able to like uncomment more of this stuff and port more from the Martinaise standard library to this. Add bytes, add arrays or buffers or something probably. Cool. Okay. Yeah. Cool. Very, very cool. Yep. Okay. I'm gonna take a break. See you then. Well, I didn't do any more coding yesterday, so I'm just gonna quickly fix this and then end this session. Right, so currently it fails because some built-ins are not implemented. Yeah, in particular these built-ins. So I think we just need to add more built-ins. The built-ins were here, I think. Yeah, int, compare, int add. Wait, what are they called? Built-in add-ins. Okay, so this will probably be add-ins, sub-ins, null-ins, div-ins, and compare ints, sure. Div mod is also, yeah, I mean, sure. Let's maybe add some, you know, like sections or something. Yeah. Okay. So we have add, subtract, multiply, divide, mod. Add, subtract, multiply, divide, mod. And then AND, OR, XOR. Then compare, yeah, and I think that's it. Yes. Cool. Next up, byte, oh, it's string. Sure. Let me just look for built-in something. Perfect. Alright, bytes don't even exist yet. That makes things easier. Yeah, converting between bytes and ints is also not necessary. Wait, but this should probably be compare ints. Yeah. And concat strings, because why not? Yeah, the byte things are up here, and when we have bytes, then we have int operations, string operations, concat strings. Cool. Built-in crash. Our stuff.
Right. Okay, that's it. I mean, yeah, we do have the type stuff, but maybe we don't need that right away. Okay, next. Put all of them into this list. I mean, sure, we can do that. Ins, subins, mul-ins, diff-ins, mod-ins, blah blah blah, XOR-ins, compare-ins. Yeah, these are all the int operations. Beautiful. Then string operations. Concat strings. Then the crash. And finally the type info. Yeah. Beautiful. Let's hope this compiles. It does not. Makes sense, because in here, where's that case add? Yeah, create built-in fun. Wow. Signature. Damn. Yeah, I think let's also put this into the built-in in here. That makes sense, I think. Oh, and we don't even need this anymore, I think. Okay, so signature of the built-in returns a yogurt. Does it? No, it just returns a tuple, a built-in signature, which is a struct with the arguments, slice of types, and the return type, a type. Cool. So this returns a brick. Oh, it just returns a built-in signature. Nice. Yeah, we have these, but then we also have modulo and or XOR. Yeah, and then finally compare. Ints, yes. Concat strings, crash, and type info. Cool. I think we don't need these because you can get that from the signature. Very cool. Very cool. Very cool. Very cool. Yeah. Ooh, yeah, sure. I mean, the instructions should also be called add-ins, sub-ins, mul-ins, diff-ins, mod-ins. What did we have? End-ins, or-ins, XOR-ins, compare-ins, concat strings. Cool. Okay. Yeah. Now this will probably fail at some other place. In the egg, well, okay. Yeah, we didn't fix the code in any way. So built-in signature. And this does not, yeah, this does not return the correct thing. Yeah, let's just do like this, and then in the end we return a built-in signature where the args are args and return type dot a dot to slice, and the return type is args and return type dot b. Beautiful. Be like beautiful. Okay. Right. So this is just a signature dot. Ooh, yeah, it should be params. Because like from the point of view of a function, the incoming things are parameters. From the point of a call, the things that you pass into a function are arguments. So these are like params. And this is the return type. Nice. Okay. I like that. Also that, you know, if we add new built-ins, we don't need to change anything in the egg. We just add them to the built-ins and that's it. And probably in the C backend and stuff like that. Okay, so yogurt. True. Yogurt. Let's see. Yeah, add ints. Is this? Yes. Sub ints is this. Compare ints. Concat strings. Type info and crash. Sure, and the others are not implemented yet, which I guess is fine for now. We have add. We have subtract. I think I'll also add multiply, divide, and modulo. Yeah. Oh. Multiply will multiply them or emit a multiply instruction, and div will divide them or emit a div instruction, and modulo will actually calculate the modulo of these. Beautiful. Okay, yeah, and now we're at the C backend where we need to translate those instructions to concrete C code. So add ins does some stuff. And let's actually like put the line break here maybe. Yeah. Like that's more beautiful either way. Well. So we have add ins, sub ins, null ins, div ins, we have mod ins. Oh, and by the way, the percent operator is not modulo in C, it's the remainder. So, yeah, let me just check. C modulo. That's what? This is wrong. This is not. It produces the remainder. Hang on. Modulo versus remainder. Yeah, modulus and remainder. Yeah, for positive values there's no difference. but the modulo is basically guaranteed to always be positive, whereas the remainder is kind of basically you ask how many times, if we repeatedly add 4 to -21 without crossing the 0 boundary, what value do we get? So this will be -1. And modulo is the smallest number between 0 and this second number, which, so that taking this times some integer number plus that is yeah, this is the remainder, not modulo. I want to have, okay, yeah, I guess I can write some C code. Oh no. This is horrible. Okay. No, this is not the modulo operator. This is there is a difference between remainder and modulo. Why is it called? Yeah, this is the remainder. That makes sense. What are you on about? Like Geeks for Geeks and Stack Overflow and C programming and Delft Stack. It's just wrong. Okay. I want like Euclidean modulo. Yeah, this is correct. Ooh, no. Yeah, meh, let's just do what? I think yeah, this is pretty much the same as hang on. Is this one? Yeah. Okay, so yeah, we basically want to calculate the modulo, I guess. And then if it's less than 0, we will want to do stuff. I'm just gonna copy this as you do, copying stuff from Stack Overflow. So what will the C code be? Basically we want to have, we have the ID, M will be the final thingy here, like the final result of the modulo operation. Okay, so C doesn't have a modulo operator, only a remainder, which means we are going to set this value to this first. Okay, and then we're going to check if this is basically n. If this is less than 0, then we want to do some stuff. In particular, we want to not do this, but we want to do this. And yeah, returning, wait, we don't need that. Okay, so the only problem is we need to replace n with this. Beautiful code. And B with this. And yeah, I could put those into variables, but what's the fun in that? Let's also just remove these because who needs them, right? But maybe add some here. So it is either this or it is this. Yes, I like that. Okay, let's actually do this. Yeah, okay, sure. And there are some other operators which we don't support yet. So we need to do that. In particular, AND, OR, and XOR. Ending ins is, oh, is it? It's this, right? OR is this bitwise OR, and oh yeah, XOR is this, I think. Yeah. Let's just compile this and see what happens. Oh, it compiles. And it compiles this to C code. Whoa. Okay, so let's maybe let's create an actual program. I mean, we do have one, but wait, I can just comment this out. Nice. Let's maybe take A and that, you know, A and 7. Or 8. Oh wait, no, those are not supported yet in the yogurt. Well, let's just take A mod 5, something like this. Okay, maybe A mod 2. That's better. Yeah, let's compile this. Okay, yeah, so we have one argument. I think this was, like, the integer you get is the amount of arguments. Yeah, we have one argument, which is the name of the program. Then if we add another one, like test A, we get 0. Yeah, test AB, we get 1. Test ABC, we get 0. Okay, so modular, for example, is working. It's cool. Yeah, okay. I think I'm gonna stop it there for this session. Yeah, we did a lot of, you know, sure, we did the casting of values, so that complicated list thingies, list castings and such things now work.
we also added some syntax highlighting and like syntactic improvements, like being able to put this on the same line, having pipes in your code, having a postfix switch and stuff like that, having comments. Yeah, lots of like small syntax things which make the code more concise. And I think we'll leave it there. Yeah, we ported some of the Martinaise standard lib here. We'll probably have to do a lot more of that. But for now, I'm happy, and I guess see you next time.